Teste, teste. Acho que foi. Yeah, because if you do not use it, the microphone is so far away here. Yeah. Do you need help? Thank you. Professor, acho que fica melhor se desligar a luz aqui da frente. É só esse aqui, né? Acho que é da atrás da TV. É. Atrás do armário. Aí, agora tá bom. Ah, perfeito.
Posso? Ok, turma. Boa tarde. Good afternoon, everyone. Thank you all for being here today, this afternoon. Our seminar talk today will be given by Professor Philippe Leclerc from UMons, University of Mons. We thank him very much to be here. It's a pleasure. We are very happy this visit this week. Thank you very much. Just a quick introduction about him. Well, last year it was a very long, so I tried to make it short. I'll try to make it very short. I try to summarize here. He's a full professor at UMons and honorary research director from the Belgian National Science Foundation at UMons, right? I took this from your member of 11 commissions of trust, including president of Royal Belgian Society for Microscopy, president of Optica, president of Wallonia Network for Technologies, right? Chairman for several conferences and scientific meetings, 300, maybe this is outdated, but 310 oral communications, 210 publications, and age index of 45. So it's a very long list of achievements. So I invite you all to read his publications, and so on. The title of this talk will be Nanoscale characterization of advanced materials for energy applications by means of scanning through microscopy and spectroscopy. So, Professor, thank you very much. Enjoy the talk.
Thank you, Alex, for this too long introduction. Good afternoon, everyone. I saw one nice faces that I saw last week in Santos and also yesterday. I gave a talk for the student. Yes, and as an introduction or a flavor of what I would like to discuss with you today. This is my second time in Curitiba. I was here last year, and thanks to a project that we got together with Alex about this is the Confab and the Wallonie Brussels School. We were happy to get this grant for 2 years, and we are crossing our fingers for the provision of this grant for another 2 years, which means that if you are lucky, you will see me next year and the year after. But it's not only the fact that I'm happy to come to Curitiba, but also the opportunity for some of you to join our group in Belgium, and now we'll spend 3 months in 2025 Camilla also came last year, Alex, and Alex will visit. So there's some money to make some exchange and to, so feel free to contact me if, and Alex, of course, to do that. So back to the science of the outline of my talk. So I just, because I will focus on energy application, I'm just making a short introduction of what are the key important parameters for energy. Then I will just show, because yesterday I spent a few minutes to explain what are the research team in LPNE, but LPNE is the name of my lab, I will explain later. Just to have a flavor of what is possible to do. I will discuss one topic today, but we have plenty of topics concerning always coming from microscopy, then some equipment, and then I will go to some illustrative example, and depending on the time, I will discuss some photovoltaics, some energy harvesting devices, and energy storage, in the word batteries. Depending on the time, I will skip one of the part of this and then some conclusion and perspectives. So if you look to the evolution of the energy and back to the pre-domestical animal domestication, the only origin of energy was the biomass. People are going to cut some trees, put the fire, and get some energy out of the biomass. Then they start to exploit animals just to use them, to help them for laboring, for instance, for the different feed and so on. And then, good or bad thing, I don't know, but we discovered the coal, and after the fuel, the oil, and now we are facing some problem because of this CO2 problem causing methane, causing different problem in this planet due to the global changing global warming. And then after that, the 80s, nuclear power came. It's not also a good solution, but less CO2. So the idea, you see the evolution with time of the global energy sources. And if you want, on one side, to see what are the energy demand that you need these days, it's about, let's say, 25 to 30 terawatt per hour. And for the moment, 2/3 are coming from the fossil fuels. And you know these fossil fuels will be disbanded. It's more and more expensive to extract them and to exploit them, but the resources are extremely. So if you look to the evolution of the of what happens now, you see this in the wind, and in yellow here, you see that the solar photovoltaics will be most probably the source of energy. Why? Because the sun is providing more than 1,000 times the energy that we need per year. So in one day you can get all the energy. Of course, you have to collect this energy and distribute this energy everywhere. It's not the fact, okay, I'm looking into the sun and I got the energy. No, you have to build some farms, for instance, collect the energy and distribute the energy where you want. So the idea, and ideally, is that 2040 is to have 80% of the energy coming from renewable. If you look to the price, this is in green, we have the nuclear cost. You see that now, because we have plenty of solar cells, solar facilities in 2030, which is almost tomorrow, the price for producing 1 kilowatt will be the same as nuclear plants. So as I said, we have defined coal, gas, and so on there, and you see they can have some energy, but you see the solar is providing 23,000 terawatt per year. So more than 1,000 times, as I mentioned before. And we can consider this source of energy as infinite for us because I'm afraid to tell you that the Earth will disappear well before the sun because of the star evolution and the expansion and so on. So it means that we will burn before the end of the sun, so we can consider that the sun is really an infinite source of energy. Another energy is trying to harvest energy either from electromagnetic waves, vibration, heat, and we can get some different processes, and this is what we are dealing with in my lab in Belgium, is to try to develop some devices and to measure locally how it's possible to harvest energy either by photovoltaics, including some perovskites, or thermoelectric properties. For instance, if you have an engine, of course, it produces some energy, but also some vibration. So the idea is to collect this energy by piezoelectricity, or thermoelectricity, piezoelectricity, and for the storage, we have this lithium battery, supercapacitor, and so on. You see, there are already commodity products. You know, these batteries you can buy in the supermarket. It's well known. On the other side, for vibration and piezoelectric, these are some emerging technologies, and we have to provide new materials. So the lab is Laboratory for Physics of Nanomaterials and Energy, LPNE, and for the people who like rock, our motto is energy, nothing else matters. Okay. With our research team that just rapidly, I discussed already yesterday this scheme. I really like this scheme because it tells that if you want to make a relationship between the structure and the properties, the performances of your device, and the process that engineers are using the material to make a device, in the middle you always need characterization. And this is really the essential of our work in our lab is to characterize these properties, morphology, mechanical properties, electrical properties, electric properties, thermal properties, magnetic properties, and so on, at the local scale. So what we are doing, as I said, morphology, mechanical, electrical, and combined properties. By combined properties, I mean you are mixing mechanical and electrical, and you have the piezoelectric properties. If you are mixing thermal and mechanical, you have thermal electrical properties. So we are working a lot on organic electronics for FETs, OLEDs, and flexible electrodes. I will discuss what we did recently for silver nanowires, then hybrid solar cells, energy for harvesting storage. I will show you some example on fibers and piezoelectric materials, and also nanoelectrics. This is related really to energy materials, energy application, but on the other hand, also measuring those properties of polymer thin, blends, block copolymer, liquid crystal to see how the molecules are packed and what are the mechanical properties at the interface between this polymer. And if you add some charges, could be inorganic, could be carbon nanotube, to make some nanocomposite and to see what happens at the interface. It could also be some fibers, some natural fibers that we can mix within the polymer matrix. So we have some industrial blends for automotive applications, for bumpers, for instance, for this kind of application. In collaboration with a group in Mons, we are studying the plasma deposited polymer. It's not really a polymer, but we have a very thin coating, and we can measure the mechanical properties out of that, which is not possible because we don't have a film. We have to measure locally. We're also working on bacteria and bioglue, and last but not least on cosmetics, with a big French company working in cosmetics. So the equipment, rapidly, now it works. Yes, it's not working. So our tools is this guy. So we have semi-pro microscopy. So the idea is to follow the topography of the sample. And how to do that? We are using this green pyramid, and the green pyramid is following the surface. And how to see at the local scale, all this tip is following the surface. You are shining the back of the cantilever, this is named cantilever, by a laser. And by looking at the position of this guy, of the reflection here, we have information about the topography. So this is the imaging mode of AFM. If you want to measure electrical properties, you just put a coating on the tip and you are measuring the current while the tip is in contact with the surface. The same for thermal, the same for magnetic properties. This is one mode of working. And we have also another mode, which is the spectroscopy, which means that you are sitting on a pixel of the picture and you are recording the force curve far from the surface. You are touching, ding, you are measuring, and then on your way back, if you have some adhesion, for instance, just now, pop, you can get information. And with this curve, you can start to measure and estimate, for instance, the mechanical properties or some other properties under the view. So these are the tools. This is cantilever over there. So this is a few millimeters. You can see those tips. It's impossible to see the tip over there because everything is occurring there, really there at the apex of the pyramid. And these atoms are interacting with the surface and are measuring the properties at this level. Okay? So all the modes that I described yesterday in detail, I just show you today what are the different modes and all the properties that you can measure: topography, mechanical, electrical, thermal, and piezo, and thermoelectricity. So we have this Swiss knife available in the lab for making use of those properties. So just some AFM. So we have classical one. This one is located within the glove box for perovskite and for sensitive material, for humidity, for instance, and for oxygen. This is another one for mechanical properties. This is why we choose the name of Newton for this microscope. And for this, we can use different items that are within this microscope. For instance, we can make some, this is for the alignment station, calibration sample, and then we can start to measure contact resonance and so on to get the mechanical properties. You can heat the sample. You can also vibrate the sample at high frequency. And with this, I will not describe this today, we can make some nanodynamic mechanical analysis that you can do at a macroscopic scale. If you remember, maybe some in chemistry they used to do that. You have the dog bone shape and they are trying to extend and to see a different frequency, what the mechanical properties are. So it's possible to do that with the AFM just by pushing a different frequency and see the mechanical answer of the sample that you are studying. So we have this system to measure the electrical properties. We have this module and we have this wire connecting the tip over there, and then we can measure some electrical properties, also some piezoelectric properties. I will come back later on the data that we can get with this equipment. We have also an electrochemical cell, for instance, to study corrosion, to study some electrochemical reaction in this closed chamber. We will use this guy today. This is an optical fiber with a solar simulator there. And this solar simulator will shine the sample, and we use this equipment for photoconducting AFM. So we have the solar cells within the AFM, and we can switch the light on and see where the photocurrent is occurring. And you know, of course, that it will happen just at the interface between the donor and the acceptor material in the solar cell, as any solar cells is at work. So this is the photoconducting AFM. And you can use also this to study the photo switching processes of molecule, as a molecule, or we can also study the first processes of photopolymerization that you can use, for instance, these SLA devices. Print some devices. This is a closed chamber that we have for this equipment, a transparent one, which means that you can use some sample, sensitive sample like perovskite, and make some photoconducting AFM on these very sensitive material. You can just purge with different gas and so on, and you have these transparent electrodes. Another view of this, we put the sample over here, and we can measure the electrical properties. Another one, which is Maxwell, not for the mechanical, but for the electrical properties, of course. And for that, we have this system, and the project that I wrote for this Maxwell was Ipanema. I think Ipanema means something for you. For us, Ipanema is a very nice building in Rio. So I had a chance last time to visit Ipanema, and I contacted the government. I took some sands. Ipanema crew. That's true. don't tell anyone that I have some sense from Ipanema, but now I have also sense from Santos. I don't indicate you who took the sand, but it was in Santos last year. So with Maxwell, it's possible to run all these modes to get the mechanical properties, to get the conductive FM, to have the piezo response, and also a new mode, which is the scanning microwave independent microscopy. And with this, it's possible to measure the permittivity and the conductivity of the samples.
Sorry.
Okay. So we have this scanning microwave microscopy, as I said. So this is a shielded tip, extremely expensive. And the idea is to drive through this shielded tip. It's a waveguide with 3 gigahertz, and we are measuring the reflection of the signal over there. Oh, I don't have this slide. And with this, it's possible to measure, as I said, the permittivity and conductivity on different samples. And there is no need on the paper to need a button electrode, because we are just measuring the reflection of the signal, and you are recording actually at one frequency impedance. You know the Z in your electrical courses that you got a long time ago, a few years ago. So we can decipher this and get permittivity and conductivity. So we have also on this system one tensile compression and bending, which means that when you have a device, you can start to apply some strain, mechanical strain, and see how it behaves. Because you will see that we try to have some flexible devices, biosensors, and these, or solar cells that you can put on your chrome. And the idea is really to measure what happens if you bend the device.
Just bend, right? Just bend.
Bend and also stretching, yes, exactly. This is a 2 mode. You have this mode. So for the moment, it's only this, like this, compression and extension. But if you put a three points, you can 2 points like this, like that. You just bend. You see, we have also an E7, and I will come back at the end. Oh, maybe this now. But I will describe, because we have also E7. You can combine FM and E7. I will discuss that later. So some examples. We are at the period of Nobel Prize, and in 2000, these 3 guys got the Nobel Prize for organic electronics, for development of conducting FM, Alan McDermott and Hideki Shirakawa. And these conjugated polymers are characterized by the fact that they have single and double or single and triple carbon-carbon bond, leading to existence of pi electron, and this pi electron can move along this conjugated backbone and leading to optoelectronic properties. So, and as I said before, the idea is to the electronics become flexible for many applications. We have some examples here. We have tags, we have phone, we have smartwatch, solar cells, also skin, smart skins, and so on. And this is one of the first pictures I got 20 years ago, almost 20 is made of oligofluorine. This is this guy with it's a kind of block of copolymer, but it's more an oligomer because we have only 8 units like this and 8 units of ethylene oxide. And I just put a droplet on the sample and let Mother Nature acting. And what we saw, some fibers. This is the topography, this is the face telling you what are the mechanical properties. And if you measure the width of these fibrils, they're about 10 nanometers. Which means that we have conductive or semiconductive wires of 10 nanometers. You can start to play and use those nanowires for applications. If you are making some modeling, the length of the molecule is about 8 nanometers. But if you look to the modeling, if you have head-to-tail packing, the width will be exactly 10 nanometers, which means that the pi-pi interaction between the conjugated segment will create those nanowires just by interaction of all this molecule, creating nanorobbon. nanoribbon of conducting polymer. So we play with hundreds of different systems coming from Europe, from the US, from Japan, from Australia, and we always find the fact that with the pipe stacking, it's possible to have these nanofibers. And one is extremely interesting is the poly-3XL thiophene, P2HT, and clearly see here very nice fibers of 16 nanometer corresponding to the length of the molecule. So also for P2HT, we have this pipe stacking information. Now we can start to play with photovoltaics. No questions so far? Okay. So for the photovoltaics, what you need, of course, is a donor and acceptor, and everything is occurring at the interface between the donor and the acceptor. If you put two layers of donor and acceptor, the interface is not that large. So the idea is to blend two materials, two polymers, try to increase this interface between the two systems, and this is what we have here. So we are blending the system here with the donor in blue and acceptor in red. We need some electrode, of course, some transparent substrate because we need the light shining the sample. We have here the electrode, the cathode, and so on, and we can start to measure. So what happens when we switch the light on? We are creating, so we have, of course, you can calculate the MO on the PSS on one side, the P2HT and PCBM, the soccer molecule, football molecule. I understand my Portuguese. And so what we have here, when the light is absorbed, you are creating an exciton. And this exciton is a pair of electron and hole, and this exciton is moving within the polymer to the interface. And when reaching the interface, it will separate the electron will go to the cathode and the ore to the anode, of course, and you can, like that, generate a current. So the idea, of course, is to be able to describe what happens at this interface between the donor and the acceptor, where the charges are separating, creating a current. If you want to increase the surface, sometimes it's better to have this interdigitated donor and acceptor, and I will show you later that it's possible to do that by considering some nanorods and having hybrid system in organic. So how to measure the electrical properties? We use a conducting AFM, and we have, in this case, what we did, we just changed the voltage, no voltage, and we started with the voltage. We can see at the bottom that we have those P2HT fibers with some black region corresponding and coming from the PCB. So what we did also, we mix with carbon nanotube just to create some highways for the charges. So the electrode is on the top on this picture, so we have the topography, we have the current, and you can see that we can measure the current out of that. If you focus on this region, this is the curly carbon nanotube here, this is the current, and we have the P2HT growing perpendicular to this carbon nanotube with a width of 16 nanometers as we saw before. In this case, the electrode is on the left side. This is the topography, this is the current. Now the voltage is positive. And not because these aggregate is not connected to the current, to the electrode, there is no current. It's one way to see the percolation of the charges through the system. So what we did, we focused on this and we changed the voltage from the bottom to the top. So we have positive, then no current, and then we have a positive. We were extremely happy with that. We spent days to find the location. We spent a few hours to measure, and we got one picture. Why? Because of this coating layer was not stable on the tip, which means that we remove the coating, which means that we can continue to get the topography, but you are losing the electrical properties. So as I used to say, so we can measure, So we got a useful information, but destructive for the organic layers and the tip itself. And to quote what David Gager, a professor at Seattle, instead of Washington in the US, patience and a willingness to sacrifice many AFM cantilever in the name of science are often necessary. Which is a good statement if you are a tip manufacturer. I don't know. But it's impossible to make science out of that. So the idea is to try to mix different things, and mixing, for instance, a peak for starting, which is a way to make some spectroscopy. So we have a spectroscopy, and when the tip is in contact, you are measuring the current. So you combine mechanical and electrical properties, and this is the peak for tapping and the peak force tune. Okay, so we are, in this case, we can measure the current. Once again, P3HT, carbon nanotube. We check that we have indeed these fibers of 16 nanometer. This is the topography, this is the current, and now we can start to make physics. We can spend days because the tip is gently landing on the surface, make the measurement, and then go to the next pixel. There is no wear of the tip on the sample, which means that you can keep the coating on your tip. Another example, P3HT PCBM. Here, this is topography. And most of the time in the literature, 20 years ago, people say, okay, we can clearly see the P3HT and the PCBM. I have 30 years of experience on chemical microscopy. This is a privilege of the age. I'm not able to tell you who is on this picture. I'm not able. Really, I'm not able. But since we are measuring the mechanical properties with that, and if you have a look to the adhesion, you start to see something. You start to see some fibers. You can see some domain. And you make a power spectral density analysis. You have two peaks. One at 20 nanometer, which corresponds to the width of the P3HT fibers, and another one about 65 nanometer, which corresponds to the average size of the PCBM domain. So what we have, you can see the fibers, you can see the domain, and we have this situation. So our understanding of the morphology of this P3HT fiber surrounding the PCBM aggregate is something like that. So this is what we think we have in our system. So the PC domain are surrounded by the P3HT fibers. So now move to the photoconducting AFM. With the sun, as I mentioned before, this is the way the light is going, coming to the device, and we use this P3HT PCBM sample. At the beginning, no light for R for the picture, and then we switch the light, and this is what we got. No light, no current, light, we have the fibrils and the P2P. And there is no voltage applied to the system. There is no polarization, no DC polarization, which means that the current that you see there is really a photocurrent generated by a photovoltaic process. Once again, we have no light and we have light here on the sample compared to the topography. There is no modification of the topography, and we have this situation. So the PC AFM is really working as an OPD. And now we can start to measure different systems, OPD system, and also some perovskite system, hybrid system, because we have the sample and we can start to measure. And another example, it's PPV, polyparaffin and vinylene with PCBM. You have the domain of PVP, a PCBM, and the PVP is there. And you can clearly see in red, this is exactly at the interface between the donor and the acceptor. So we have negative current on the crystalline of PCBM. This is and a positive current just at the interface between there. You can see clearly this interface there. And this is why we have this information about the photovoltaic solar cells made of this compound. I mentioned before that we have this possibility to have an interdigitated system. So what we did, we used TiO2 and we make some nanorods out of that by using a kind of shadowing effect. So we have deposit and we have slanted, and we have the possibility to create those nanorods. And we equipped the P3HT with carboxy group here, and you can this group can just fix on the TiO2, we make some modeling to show that indeed this is the case, and we have one polymer change just attached to the TiO2. So this is the way to do that. So we have the bare TiO2 on ITO, we drop cast the P3HT, we remove, and so we rinse. In fact, what we have TiO2 covered with the P3HT. This is what we have for TiO2. And so we put, here we have the topography, no P3HT, we just put in the solution. So we have P3HT on the right, no P3HT on the left. On the top, no light. On the bottom, light. What happens for the photocurrent? Where do we have to see some current? Everywhere? Yes? Where? On the bottom? Left or right? Bottom right, where we have TiO2, the light, and the P3HT. Okay, and you can start measuring. You can also make some KPFM for microscopy. Because some people are measuring not the current, but the voltage out of the source cells, and we have the same situation here. So we have the topography, the adhesion, potential, and you see a big difference in the potential when you are switching the light. For the perovskite, you know that the problem is humidity, and so we did in our group is to compare different groups to prepare those perovskite. And perovskite the same some recipe of caipirinha, or recipe of something. Each family has its own recipe, and it is the same for perovskite. So we compare two recipes, and this is the acetate route. So we are using this compound, drying and heating. And there's the lead iodide there, route. And it appears that one is extremely stable with time. So to do that, what we did, we in the two routes, we measured topography, the work function with KPFM, and the current with the photocurrent, as I mentioned before. And this is for this route, and this is for the other route. We have the work function and also the current. And then to see what happens when we have some water, we put the FM in an ALD chamber, atomic layer deposition, in which you can control layer by layer the water coming on the sample. So what we did, Joe made it actually. This is for the lead acetate. You see that work function is moving, evolving when you have 10 layers, 20 layers of water, and the cycle of water means layer of water. You can see the evolution of the photovoltaic, the photovoltaic, which is extremely annoying. And if you consider the lead iodide, you have very stable with time with this, the pattern of the water. It's possible to do that. Just make some slides about the transparent electrode. I told you that we need flexibility and transparent electrode because it must be conductive and transparent because you need the light to get in if it's a photovoltaic and to get out if it's light emitting light. It's quite interesting. And most of the time people are using ITO. Extremely have high cost, scarcity of indium, so the idea is try to replace that. And one of the elements which is the more conductive is silver. So the idea is to make some silver electrodes, some silver nanowires. This is what Dieu did, that was PhD last year. And the idea is to make some nanowires, this is the solution. And the idea is to optimize this figure of merit, where we have the electrical and optical properties. And this is what is down in literature. So the idea is to have a very low sheet resistance and high transparency. And you see for graphene, for single one nanotube and so on, copper nanowires and silver nanowires. This is the work of Dieu. So we have very nice figure of merit by using these silver nanowires. The problem with these silver nanowires is the interaction between two silvers. Because it's connecting on one wire, nanowire, but when it's crossing, you we have the difference. So the idea is to have a very intimate connection between the two nanowires, so to increase the contact area between the two. And so to do so this is what you measure. So this is photography, no current, no voltage, no current, we start to see some fibers there, some nanowires, sorry. And then if you put too high voltage, you are just melting the nanowires and no way to. So we have to find an optimum, which is about 600 millivolts. So the idea now is to improve the contact area between the two crossing nanowires, is to make some electrochemistry, and this is what we did. And now with that, we consolidate the nanowires and the connection between the nanowires, and we can start to use them to measure some percolation pathway. So we have the electrode over there, the LTO, one nanowire. This one is just in Y junction with the blue one, and this one is just below the blue one. And you see that this is the resistance, which means that low resistance, high current, and you see now an increase of the resistivity, so low current over there on the red nanowire. So this is what we have in the 3D rendering. We have the ETO, we have the nanowire, you see the other one, and so that in these one are not connected. They are present but not connected to the electrode. So by playing with banding and with the mechanical strength, you can see the stability of this system. And we can use also this electrode for light emitting diodes. So there is here the electrode with nanowires. This is the end of here, the electrode. And this is the orange OLED that we recorded, we developed with the Okay, some slides now about energy harvesting. So the idea is to use piezoelectric application, and you know there are plenty of systems that you can use, either ceramics, polymers, or crystals, and all of them have some applications: sonar, acoustic device, actuator, or sensor, but they have also some properties and drawbacks. For the ceramics, high piezoelectricity, but are extremely gradable. For the polymer, low piezoelectricity, but flexible, thin, light, easy to process, and stretchable. So you know why we are using polymer, because for the flexibility of the device, of course. And for crystal, very low piezoelectricity, but extremely stable, which means that, for instance, for fire detector and so on, because there is no constraint, we can use those crystals for measuring the piezoelectric or thermoelectric, because they are stable, just in small box. And if you compare all the piezoelectric materials, PZT, there's a lead, and this is extremely toxic, so the idea is to replace this lead by other compound. It could be BTO, it could be NBO3, or some polymer like PVDF, but you are losing a factor of 20 with the properties, but this is a compromise. You have flexibility, you have less possibility, the properties are lower, but you can manage to anyway collect some information. And of course, you know that piezoelectricity coming from, you can polarize, you can deform the system, or vice versa. If you're deforming material, you create a polarization and can create a. So how to do that? Using scanning probe microscopy. Let's imagine that you have polarization and the electric field is like that. You are pushing, so you are in phase. The driving voltage, the piezo response is in phase, or in the opposite, if the material is the fact that when you are pushing, the polarization is anti-parallel to the electrical vector. You have out of phase, and of course we have all the intermediate situation. So what you do is to apply a voltage. You have expansion or contraction of the material, and the tip is just following the difference. You are sitting, you are measuring positive or negative, and you can see the deformation of the sample when you apply the voltage to that. I will not enter into the details, but the idea is because you have generating charges when you switch the voltage on, it's better to measure when there is no charge injected. So I'm injecting, measuring. That's why we have this this strange write and read voltage. You have this kind of stairs, and you are measuring when you are not applying voltage. And from that, it's possible to have this piezo force microscopy response, the hysteresis loop, and you can start to measure different parameters. As I said, there are plenty of artifacts in the literature and the medical. This is the worst measurement you may use with spherical microscopy, is the piezo. It's extremely complex, because there are plenty of artifacts. You have electrostatic effect, because the cantilever is collecting. And you are measuring at the apex. If you are not shielding the tip, you are measuring also the contribution of that. And the tip don't care. There is an electrostatic force. I'm going down, up, or down, and this is what you are measuring. So to extract the D33 or the piezoelectric coefficient is extremely complicated. There are plenty of also electrochemical strain, electrostriction, and so on. So it's extremely complicated. It appears that if you are putting, when you're starting with AFM, if you want to have high sensitivity, it's better to put the laser at the very end of the cantilever to have the maximum of energy, maximum. But it appears if you put this spot at more or less 2/3 of the maximum, it means that you compensate the electrostatic force. It is the so-called electrostatic blind spot, ESBS in short, and with that, you almost show that you are measuring correctly. I can show you a lot of papers claiming that you have very huge coefficient of piezoelectricity for a lot of artifacts because they never measured anything. And the problem for the moment, if you are measuring correctly the properties, you are 1 order less or even 2 order less than what it was published. And it is really a nightmare to show and to prove that what we are measuring is the actual value and not the value measured non-intentionally by people they measure. They didn't know about the artifact. They say we have a coefficient of 300 and you are measuring, for instance, 30. And the actual value is maybe 40. It's extremely complicated to measure PFM, but it's doable. So the idea is to replace the lead, and the idea was to use, for instance, zinc oxide nanowires or nanoparticles. Why? Because it's not toxic. It's a green material. It's to synthesize cheap, and you can sorry for the misspelling. It's morphology, and we can use for many applications. And this is the work of Imen, that Camilla knows, and this is the ESAM, and this is the AFM. And this is what Imen was measuring macroscopically. So we have something like 7 picometer per volt, and with AFM, by using the technique I described before, we are about 6, so we are not far from at the local scale what you are measuring at the macroscopic scale. And you can play on this nanowire, you can push like this, and measure the piezoelectric properties. So we have those nanowires, hexagonal nanowires, grown with hydrothermal processes, so low cost, as I said, and with very low impact on the environment compared to the lead-based system. And this is the FM, this is the SEM, and you can measure. And now the idea of man is to land on one of these nanowires and start to measure individual properties. Another and the last example, I will skip the battery stuff. This is electrospin PDF and BTO. Maybe they will be interested by this. There's nanoparticle. So this is the SEM. So we have a PDF, and inside you can see some aggregates of BTO. This is another example made by Pierre. This is BFO, bismuth ferrite, within PDF. And you can see on the electron microscope that we have some BFO aggregates. So this is in gray. We have here the PVDF, DRFE, and we have some particles of BFO. Then we go for AFM to measure the electrical properties. So this is the topography. This is the the phase. You can see some BFO here, and we have this PFM hysteresis loop, so we know that we are sure, and you can start to measure the properties of these nanoparticle, piezoelectric nanoparticle inside the system. And this is in high concentration. We have here the answer of the PVDF and here the answer of the BFO. Why the cycles are different? Because one is positive, or is negative. But by compensating, by playing, it's possible anyway to get some properties out of that. This is another example with spaghetti-like PVDF fibers with some PFM inside, and we can start to measure. This is the mechanical part, and this is also the phase here. We can see some BFO inside the PVDF fibers. Okay, I told you that I skipped this. And then just a microwave impedance microscopy, as I showed before. Slides coming out. We have 3 gigahertz. We are measuring the reflection here, and we are using some electronics to decipher the amplitude of the phase. You can see the evolution of the capacity or the resistivity, and you can map this the different properties on the flake sample there. So, in conclusion to this talk, I try to convince you that connecting FM, KPFM, E4 tuna, you can get high resolution picture. You can describe what happens not only on the morphology but also on the electrical properties and the photophysics on okay, yes, the batteries, but you can describe what happens in the photovoltaic solar cells. This is, for instance, one example of silver photo ablation of silver nanowires dispersed in the polystyrene matrix. And you have in red the polystyrene, the silver nanoparticle over there, and in blue we have the interface, which is extremely important in nanodiodes to improve the properties of those nanocomposites. And finally, in terms of perspective, we soon have this equipment we can put inside the SEM to make some correlative probe and electron microscopy. So we have the FM, different mode, SEM, and the SEM is equipped with EDX, so we can have chemical information about the data, and we can use this system to merge and to correlate those AFM measurements with the SEM and to get some information. And soon also we have the nano-infrared, which means that sitting on a pixel, we can start to record one spectra and say, okay, for instance, this is the blend of polystyrene and polystyrene in orange and in green polyethylene. And you can either make an imaging and what given frequency, and you can see, okay, if we have some highlights, it means that recognized compound, or we are sitting on one pixel and you can record the spectra and you compare the spectra with a database, and you can say, okay, you can identify this. This is extremely important, for instance, for microplastics that you can unfortunately find everywhere in our river, in our ocean, and so on. You can see and identify the origin of those polymers. You can do the same also with Raman spectroscopy. So we have all these modes, AFM, AFM with the sun, AFM with infrared radiation, AFM with a mechanical strain, and you can combine AFM with scanning electron microscopy. So the take-home message, if you want to work and if you're working with devices for energy application, you need, of course, the better understanding on the fundamental mechanism of the photon-electron conversion, the design of new material. You have to tailor the energy levels, solubility, morphology. You have to process to create some nanostructures, use some analytical tools, including, but not only scanning chromatography and scanning microwave impedance microscopy, and then to optimize the architecture of your device to optimize the properties. So this is definitely an interdisciplinary approach to solve this problem. Obrigado.
Thank you, Professor. So, questions?
So, can you go back to 50 or 60? Please.
designs.
Yeah.
61.
Maybe
65.
okay. When you show the images by current, all generated by photocurrent.
Okay. Like this one.
Okay,
Like this
it's
one.
kind of there. One of the biggest problems we have with organic power is stability or lifetime. So this could be easy to measure stability or lifetime, and beyond this, we can also put in, for example, some optical microscopy and consider effects like photoluminescence and merge this to study stability or how my polymer can improve if adding some doping or additive.
Yes.
Could be possible because we have a lot of challenges.
Exactly. Yes, concerning the lifetime, I didn't have the time to do that, but what we can do is to send a pulse and continue to measure the decay of the current. With that, we can try to estimate the lifetime of the charges by probing, by shocking the light. For instance, a different frequency. We have some papers that is people going on. So it's possible to extract the lifetime like this. Even if the measurement is slow, if you are shopping, you can average and use the model like this, the decay of the current like this. And of course, since we have the chamber, we can start to play with humidity, with temperature, and see the stability of the. The only problem is sample preparation.
Oh, yes, correct. That's some works including, I'm just mentioning about that, and try to add in some additives or doping, as said.
Yeah.
For example,
Iodine.
red set, red set, regular side, and it could be possible investigate in which sites these additives are included. For example,
Yes,
or
if for instance they are not too small, if they are not too visible with the polymer, and if they present one physical properties, being the adhesion, being the model, the rigidity. If you remember the slide with the P2H2 fibers and the PCBM, it was possible from adhesion to decipher with fluid. So once again, if you put some additives, you will see either the mechanical properties changing locally, and it's okay, most probably the additive is there, increasing or decreasing the properties. On the paper, it's not complicated. If you have one property that you can create a contrast with, and then after you compare the topography and this channel with the, it could be also the chemical signature with nano-infrared, with infrared. If you have a region rich with this dopant, you will see the contrast between dope and non-dope. Locally, I said it's doable if you find a way to decipher the compound. Take a rigid polymer and a soft polymer from the mechanical properties. It's just like the nose in the middle of the figure.
and this measurement could cause in accelerated degradation of this material. We can control them.
No, you're right, because you apply voltage and you can, of course, you can destroy the layer. But the idea here was to show that we can generate photocurrent out of the system. And but for instance, for the perovskite, we worked a lot on the stability of the perovskite by controlling the atmosphere around the perovskite.
Oh yeah, thank you for the talk. I just curious if you can coat the conductor in AFM with carbon nanocones, the way that you can, because you have a metal on top, right? Your tip is metal, so if you cover with carbon nanocones, it could protect the tip.
Yes, and some people are doing, you can use carbon nanotube to have a very thin, we discussed that yesterday, but of course you can coat the cones ideally you have to find one code which is protruding lower than the other and use this as a tip. The beauty of that is some people are also using some doped diamond powder, which means that if you are breaking the tip, you still have one conducting stuff that can do the job. Or some people are using PTSI, tip, which means that you are breaking the tip, but you keep the electrical properties, the conductivity of the tip, to avoid to have this coating. But the best is to have the coating, of course, and try to keep it alive a long time.
But the presence of this diamond powder couldn't affect, for example, the direction of the probe.
No, it's just really coated on the tip, and only the apex of the pyramid is interacting with the point. You are losing resolution because you don't know the shape of the. It depends. What do you want? You want to describe the physical properties or the morphology and the mechanical properties, which means that you can visit your sample with different tip, different approach, and make a corrective analysis afterwards. This is what we are doing now. For instance, if you want to get the nano DMA, because to record one image for the mechanical properties, it takes, let's say, 5 minutes. If you want to make nano DMA for 1 pixel, it could be 2 minutes. Which means that if you need to make a 500 by 500, you will take 3 months to take a picture. No need. Just take a picture of microscopy, 5 minutes. You see different region. You just then take one picture, one spectroscopy there, and there, and get the information.
And you also can change the temperature.
Yes.
So this could be possible. See, have some change of percentage, just taking
Of course. We did that a long time ago on polyethylene and on polyethylene oxide at 60 degrees. You see the creation of the cold crystallization. Totally doable. It was not the topic of today, but we did that 20 years ago.
Any more questions? Brenda?
No, so you write, I think it's the slide just before this one. Which is the phase of this TiO2 synthesizer?
It's annotated. Yes.
So there's it's almost like a plane you can do with the TiO2. When you build the different stoichiometric proportions of TiO2 in different phases, you can have these tree-like shaped structures, and it can improve the area of these electrodes.
Yeah.
So, have you ever tried of doing
No, we did that during the thesis of Laurie, which is because 6 or 7 years ago she left for the moment. But, I like this example just to show that we need by covering the TiO2 with PhD and photovoltaic.
I have just one more question. You said you can adapt the SEM with the AFM, right?
Yes.
I don't know if you have it, but can you like adapt a cathodoluminescence spectrum in there?
If you have a detector to put on my SEM, I would be happy. No, it's really
You could do that.
Yes. We don't have for the moment. I think we can put this as a quad growth from Thermo Fisher. And the guy came to my lab and said, we still have one window to put one detector because we already have plenty of detectors. I described them yesterday, but of course, yes, in principle, the possibility exists just to put this. You have an SEM, and then you can put the FM to make some correct analysis. Good point. Is it expensive? You can buy one before you come, right? Is there any question?
Any more questions?
Very
Can you improve the time resolution because you need some time to take picture? So I believe that this would be the next state of the art in this kind of.
Yes, we discussed that yesterday. Some people are measuring video rate to see, for instance, the folding of proteins, the prices, which means they are extremely fast to measure. we are losing resolution, but you can see the shape of DNA moving or some proteins moving. So it's certainly doable. This is the fast scanning, but for the moment, only few groups can do that. It was invented in Japan, in Canada, Ando. And now it's difficult. I mean, they are improving the equipment. It's possible to make some measurement, but you have to go there. It's not already commercially available. Fast scanning is existing, but not really at the point that we can use slow science.
What is the time scale for the
For the acquisition, it's about a few minutes, as I said.
wow,
Few minutes to get resolution.
compared to picosecond or something?
Of course, but if you want to analyze one brand and you mix with polymer, few minutes is okay. Compared to SEM, to get very clear. But if you go for STM, for instance, you can spend one day to get one picture. Here, you can report in a few minutes. You can ask Camille, she knows how to operate in the
And how far you can go in terms of spatial resolution, within
Depending on the
the near
technique,
future?
depending on the technique, depending on the tape, because if you want to have just morphology, you can go down to 1 nanometer. If you want to measure the mechanical properties, it's much better to have a spherical tip and you know the radius, because you use the radius for the modeling. Let's say you take a tip of 30 nanometers, for instance, you have 2 nanometers, you know exactly what is the contact area. From the contact area, you can use modeling, you can have quantitative values. But you are using resolution, but when you are probing a polymer, you know that you will get the information. If you want to take a very sharp tip, you can have resolution, but you don't know what is the contact area when you are examining. So it's a compromise, resolution and quantitative measurement. While what we are doing in the lab, we are making high resolution and revisit some place to get quantitative value in the photovoltaics or the mechanical properties. But 1 nanometer is in ambient condition.
But this could take some minutes, for example, to get a real image.
The first image will take you 2 days, and after a few months, it will take 5 minutes. It's a matter of sample. If the sample is very flat and well perturbed, then you can get, if you miss some information. Typically, we take 1 line per second, and it's 512, so 512 seconds, which means you can go faster, you can take less pixels from the picture, but it will be detrimental for your resolution. The more data you can get, the more statistics you can use, and you have data for AI analysis. It's always compromise.
Any more questions? Okay. So, thank you, Professor. And
Obrigado.
thanks.